Hi, in this video we're going to discuss logistic functions. So in real life we have situations when we have what's called limiting capacity for growth, and we use logistic functions that are going to look like this. And some of the facts that you need to know about a logistic function: it's increasing, it's going to have two horizontal asymptotes. One of them is going to be at x equals 0, the other one is going to be at x equals a. That's the top value. We call it the limiting capacity. This function is bounded, but it has no minimum or maximum value, because with the two horizontal asymptotes the function is going to continue approaching those values depending on whether you go to the left or to the right. It does have a y-intercept. At this point it's going to be 0 comma a divided by 1 plus b. The limiting capacity is often called, when you apply it to population problems, it's often called maximum sustainable population. And also, there's something interesting about the curve of a logistic function. There is a point of maximum growth rate that occurs at half the limiting capacity. So before that the function is increasing at an increasing rate, and after it it's an increasing at a decreasing rate. In calculus there is a name for such point that's called a point of inflection. The curve that we're talking about of a logistic function is going to look like this. Okay. So this is the limiting capacity here, and that's the other asymptote. That is going to be x equals 0. Alright, I only have a couple examples here. Catfish was released into a pond in 2000. Its population is described by a logistic function c of t, where t is a number of years after 2000. Here's our function. What was the initial population of catfish? How many catfish was there in 2010? What's the maximum sustainable population of catfish? And in what year does it reach its point of maximum growth? Well, one question we can answer without doing any math is C. The maximum sustainable population is going to be the top value. So it's going to be 5,000 catfish. Okay. Now we need to graph this. So when you graph this, you need to go in your calculator, and it really depends on what calculator you use. I'm using TI-84 here. So I'm going to have to put this equation in here. So I'm going to type in 5,000 divided by, put the rest in parentheses, it's going to be 1 plus 124 e, if I can find where my e is, e to the power negative 0.4. Well, it says t, but we have to use x. And okay, here's our function. Now we need to graph it, first of all. And here's the trick about graphing. Probably you might be in the standard window, it might be in the window that's not going to accommodate this function. So what we need to hit window. And for my x values, I'm only going to go from like 0. And for my x max, I'm going to go to all the, well, I don't know how far I'm going to go. Let's just make number 30. That's going to be 30 years. But over here, so y min is going to have to be 0, but y max has to be 5,000. And since we're going that far, I would probably change my y scale to maybe like 100. And now we can hit graph and take a look at this curve. So right about here you have this point of maximum growth, halfway. So it starts increasing faster and faster and faster, and then it starts increasing slower and slower. So let's answer our questions. What was the initial population? The initial population is when t was 0. So if we go to our math feature, so we can go to second calc and enter value and press 0 for our x value. Our initial population was 40. So the initial population of catfish was 40. How many catfish was there in 2010? Well, in 2010, that's 10 years after the year 2000. So what we're going to do is we're going to do this again, second calc, value, so it's 10 years later, and the population was about 1,528 fish. Okay, how do we answer this question? The last question, it's asking us in what year we reached the point of maximum growth. There is a way to do it without a calculator, but there's a way to solve that as an equation, but I don't want to do it in this video. So what I'm going to do is I'm going to do the following. I'm going to graph another function that's going to be halfway. Remember, it's at halfway, so it's 2,500. And I graph them now. So I have this line that passes at exactly half point between the two asymptotes. And what we're going to do is find the intersection there. So we're going to go to second calc, intersect, and we need to select our curves, second one, and now we need to select our somewhere near our point, and our intersection is at about 12 years. So about year 2012, right? So about 2012, the population reached its maximum growth, right? Okay. I have another problem very similar to this one. Now we're dealing with population of wolves on an island that's been increasing since 2010, according to the logistic function W of t, where t is the number of years after 2010. This is our function. And we have questions: what was the population of wolves in 2010? How many wolves will there be in 2026? What is the maximum sustainable population of wolves? And in what year does it reach its maximum growth? Again, there's one question we can answer right away. What's the maximum sustainable population of wolves? That's that number on top, so it's 560 wolves. Okay. And now we have to enter our function in the calculator. So let's go ahead and do that. So delete that, delete that. It is 560 divided by 1 plus 13 times e. Nope, that's not e. This is e. Sorry, I missed it. To the power of negative 0.28 x. Remember, we're graphing, even though it says t, we have to use x so we can graph it. So that's our function. Remember, we have to adjust the window. So we're going to go to window, 0 through 34x values, that's our time, it's probably going to be okay. But 0 to 5,000 is going to be a lot now. So let's change it to 560. I'm going to change this value here to 50. And graph. So there we go. Very similar curve. Let's go ahead and answer the other question. So what was the population in 2010? That's the initial population, because we started looking at that since 2010. So that's a value of 0 for t. So if we're going to go to second calc and plug in the value of 0, that's going to give us 40 wolves. How many wolves will there be in 2026? So 2026 is 16 years after 2010. So we do the same thing, only put 16 for that value. So we're going to go to second calc, take value, and type in 16. And we're going to be at about 488 wolves. So 488. Alright, and then in what year does this reach its maximum growth? We know that's going to happen at halfway of that number, so it's 280. Let's go ahead and press y equals and type in the horizontal line at 280, graph it. So right here we're going to have our maximum growth at this point. Alright, and we're going to find that intersect. So second calc, intersect is option 5. Select one curve, another curve, and bring this a little closer to our intersection. and our intersection is going to be at about 9, so it's about 9 years, about 2019, sometime in 2019. So I do want to mention one other thing really quick with regards to this problem. Please understand that what we're dealing with here is a situation like, for example, with, if we go back to this catfish, you put catfish in the pond, you are going to the population is going to start growing, but what happens at some point, because as you get more catfish, you're going to start running into a situation with limited resources, space, and also food. That's why it cannot continue growing faster and faster and faster the whole time. At some point, that growth is going to start declining. The same thing happens with wolves. They're going to have to find some food on the island, and that's just going to be as more wolves are on the island, then that becomes more and more challenging, so that growth cannot continue on forever. Okay, and I hope this was helpful.